descending to the surface of our world to test the force of gravity. After contemplating a few locations, I've decided the best is out here in the Mojave Desert along the Californian Aqueduct, an excellent location as you will see shortly. Here we are on the surface, folks. I parked over there and I walked along this walkway by the aqueduct, and from Google Earth this surface is at the same elevation. It does not slope, only the water flows down this trough, the aqueduct, but this walkway is actually level and straight for a few miles, and then there's another pump station. It was a bit windy, but here's my instrument, a telescope and a high accuracy inclinometer, 0.001 degree resolution. With such accuracy, I can carry out this experiment in a shorter distance. I don't have to walk with all this gear for too long of a distance. Here's a closer look at the instrument I'll be using. It's a 480 millimeter focal length refractor telescope that I'll be using to sight objects in the distance through the infrared camera Alpha 6000 converted to 830 nanometers. And I'll be using the zoom feature on that to really zoom in and align that telescope. And then I'll be measuring the inclination of the telescope with the ultra high resolution inclinometer. Here's the theory. I'll be measuring the divergence of the gravitational vector. Our theory says that we live on a ball and gravity radiates out from the center. So if I move along a straight line on the surface, the angle that the gravitational vector makes with that straight line will change from place to place. If the Earth is flat, then theta 1 will equal theta 2 and also equal to theta 3. In other words, the gravity vectors will be parallel and they will not diverge away from some imagined center of the planet. To minimize the errors due to surface flatness or lack thereof, we need to align the telescope to a distant target. And here I've calculated that for a resolution of 0.001 degrees at 54 miles, which is where I've sighted a good target, the variation can be up to 5 feet. And we would still be under the measurement error of the inclinometer. So the aqueduct actually is quite a flat surface, varies less than that. So I have pretty much eliminated the contribution to the surface variation. Now here you can see where I've parked, and then I've walked from there and aligned the telescope at 6 different locations labeled as S1 through S6. Now the horizontal variation there is about 1 mile, slightly over 1 mile. This location by the aqueduct is perfect because it is a flat level surface, and also because we are high above the desert floor, so we're not sighting through the turbulent air due to heat gradients, temperature gradients above the desert floor. So I am really excited about this location. Now, here's how well I can sight an object with the telescope and by zooming in on the camera. I have chosen the quartzite mountain about 54 miles away because it has some antennas on top. And I can pretty much align it to about 0.002 degrees to be conservative, maybe slightly better than that. Here I'm walking back from the distant location, site 6, which was across this road I just passed. This is to give you an idea of this vast open area, and see, we're actually high above the desert floor here. And according to Google Earth, this walkway is actually very straight, incredibly straight, probably changing less than 1 foot per mile. Just incredible. So a perfect ideal location for this experiment. So here's the results that I gathered. I recorded the measurements on my phone, and initially the first two sites, the number varied quite a bit. And as I went along, I kind of perfected the method. At site 3, I realized I need to pay a little bit more attention to how I align the telescope. So when I walked back, I redid site 1 and 2. Now I discovered that the two parallel surfaces of the rings that hold the telescope, as you can see in the lower right, are not exactly parallel. And so the inclinometer would toggle slightly. As you can see there, you can form two triangles that would be flat, right? 3 points specify a plane. And so because the two ring surfaces on top were not quite exactly parallel, the inclinometer would toggle slightly. And so then once I discovered that, I paid more attention to it after site 3. So anyway, I went back and redid site 1 and 2. And the first column is the x-axis. So basically rotation about the x-axis. And that's the number we're interested in. The y-axis was, somewhat aligned close to 0, a degree off here and there. But it's really the x-axis measurements that we're after. Now here's the incredible results that become apparent once we plot this data. So the green curve is what the globe says the angle should be, reference to the first point, station 1. But notice our data in blue, it varies due to the measurement errors, and there's the error bounds, but it appears to diverge away from the green line. And if I would carry out this experiment to longer distances, that difference would become even more apparent. So what this means, folks, is that there's no variation in the gravitational vector. All the vectors are parallel. There's no divergence, which really means our world is flat. This is simply incredible, folks. The Earth is flat indeed. It is incredible. It is a mystery, but it's reality. In the lower right corner, I've tabulated the data, and I've also calculated the height of the mountain I'm observing based on my measured angle. That's column 3. And notice it's fairly close to the actual height of the mountain, which I obtained from Google Earth, about 500 feet off, which is not bad considering the fact that this is not a calibrated, telescope axis relative to this inclinometer. but it still works because this bias in the calibration affects all the points, and this measurement technique is actually really great. We can even have a slight slope to the surface and it still works as long as it is a optically straight surface we're measuring along, and there's no variations in the calibration of the instrument. This experiment still works. It is really incredible. So there you have it, folks. There is no divergence in the gravity vector. Thanks for watching this epic presentation, folks. Please comment down below if you've enjoyed it. That's what keeps me going, folks, your comments and support. So thanks again and God bless you all. Stay tuned for more incredible content coming your way. God bless.